Good morning to you all. I wish to thank the chairman for giving me the opportunity. So I'm a West to talk to you. So I'm a West Coast guy, as as Mr. Chairman said, and I'm going to present you this approach to urban air quality monitoring that is based on a maker-friendly mobile and social sensing tool. And we have seen, this is the outline of the presentation, we have seen the very outstanding presentation of this morning calling for an increase in crowd sensing and the exploiting of the data that are produced from this kind of application. And this can be also applied to urban air quality monitoring scenarios. And we can see that this new concept of citizenship is spreading in the US and the EU, and the citizen want to be active part of the intelligent management of their environment. This is particularly true also in our environment in the south of Italy, where the relationship among the public authorities and the citizens has been very challenged in the last few years. So people would be very happy to participate and to have his own sensors gathering data about the environment. Of course, we have to understand that the current situation of the air quality monitoring in our cities is based on official organization gathering very sparse data with networks that are constituted of very few nodes. So it is not possible to gather a real picture of what is happening in the city because of a lot of nonlinear effect caused by the topology of the city. But the availability of low cost and low power and portable personal analyzer is growing. So this may help to densify this network and eventually enable good policies to be implemented. So what we want to propose in this paper is to move further, to go with to analyze the possibility to use open source hardware and software to build a sort of ecosystems to fuel this kind of application, particularly in the air quality scenarios. So the route that we want to follow is to provide a way for the citizen to obtain or build their own sensor node, then quickly start to participate to the air monitoring challenge. There are a lot of competing research that are ongoing in this field at this moment, especially in the US. But we have also, for example, the Everywhere project in the European Union. But a lot of other projects have been presented by the chairman. And but a lot of them are not open, so it is impossible for the user to build his own solution, and also a lot of detail are not very detailed, so it is impossible for people to join unless officially joining the program. Another challenge is to manage the large amount of data that would be produced. So we want to understand if it is possible with open source technologies currently available to build such an ecosystem. And of course, the basic problem is still coming from chemical sensing, because it's very challenging for both a lot of for problems and issues produced by instabilities and the specificity of the sensors. The architecture we propose is very simple. So it is based on a sensor node that connect to a mobile device, and this mobile device may provide an interface to the user, and at the same moment the data that are gathered from the sensors are sent to a backend, and with which another user can interact for understanding gathering the data, that gather a picture of the data that has been sensed by the users that are moving in the cities. And this architecture is very simple. It is also very modular. It is possible to change the specifics of one model without affecting the whole system. And we have to provide a way to improve semantic value by starting from the raw data gathering by the sensors and to arrive to a 2D human computer interface that reconstruct a map of what is happening in the city with regard to the air quality. And we have two main points that we have to analyze, but in this presentation we will focus a little bit more only on the onboard calibration model, because the sensors should be the data gathered by the sensors should be analyzed and calibrated to provide an estimation of the real concentration. And this data can be are then sent to this remote storage, and all the data gathered in this remote storage, and then this data are used to by different models, can be used by different models to provide this 2D map, and this can be called as a model as a service architecture. Look, that one of these can be also can also take advantage but weather data and air pollution model data with the data simulation uh, approach. The census node that we have used at the moment are based on two possible choice that we have we made. One is based on the gas census board provided by Libelium, that is a pseudo open source solution based on metal oxide sensors in which both the hardware and part of the software are open source. And the other one is an ad hoc open design designed by us, exploiting the AlphaSense electrochemical sensors connected to an Arduino clone that is an ST microelectronics Nucleo system. As regards the Libelium, we can see that these are the sensors that we use at the moment. These are the Figaro, so it's the Japanese sensors TGS 2442 for the CO. Another one is the mixed sensors 2710 for NO2, and the mixed 2610 for the O3. Plus, we have added RH and temperature for sensors response compensation, multivariate calibration. With this architecture, we've been able to reach a 60 hours battery lifetime. Our concern was about the use of this kind of sensors is generally coupled with a high power consumption, but by using temperature modulation, not temperature modulation, but temperature pulsed operation, we can reach 60 hours of battery lifetime that is compatible with the use with the smartphone. So at the moment we are using off-the-shelf calibration, but we are also in progress on-field calibration of this kind of node. The second stage is characterized by the application, the Android app, and so we can see that the node that is whose case has been 3D printed send the data via Bluetooth to the smartphone, where an Android application is capable to provide a local calibration, what we have underlined here, and the data are then sent to the storage. At the same time, the Android application should try to allow for the user to assess his personal exposure while moving in the city. So we have resorted to the mobility session concept, in which the mobility session is the time in which the user is moving inside the city, gathering data, and in this by using synthetic data, by using time integral of the EPA air quality index, the user can assess his personal exposure during mobility, and these are the different snapshot of the interface, in which the user can see the while moving the the estimation of the um, concentration of the pollutants that is facing, then he can use the georeferences data to build the path and understanding where he has been exposed to a greater part of his pollution index, and then also a graph of the gathered data. As regards as the as the calibration, but more of this when will be given in the next presentations. We have chosen a calibration model based on multivariate calibration and neural networks, and one of the main challenge for mobile application is to cope with the dynamic of the sensors. One possible way to become to understand what is the performance level that we can reach is to use fixed station, but located at very close to the road sign. And this has been possible by looking at data given courtesy of the University of Cambridge and the chemical department specifically. Um, what we obtained here is something impressive, because the mean absolute error that we can reach with this multivariate calibration is about 1 ppb. That is very impressive, very impressive at the moment. This data have been gathered along 5 weeks, and 1 week of the data has been used for training the neural network approach. And these are a graph in which we can see that the resolution and the quality of the estimation is very data by comparing is quite impressive. And by comparing the red line and the blue line is the data gathered by the traditional analyzer that is collocated at this road intersection by the estimation provided by the network. And we can see that the correlation is significant. And actually, the correlation coefficient found is 0.9. As regards the choice of the backend server, we have resorted to a NoSQL database structure as a most suitable one, because traditional RDBMS has shown have not been designed to cope with the scale and agility challenges that this application has, and in particular they are not scalable. This is very difficult to scale up the system when the gathered data is growing. And we have found this solution as an open source solution for the kind of application, and we have resorted to the MongoDB NoSQL database application. And what we actually do to communicate to MongoDB is to resort to RESTful design, and basically the data are posted with HTTP GET and POST. Okay, so the web application the web application that we have built as third layer can be used to retrieve data and to generate the map on the server, and to browse them in the client. And it's really it's important to understand the limitation of this approach. Of course, we have the data that we have gathered in long-term experimentation let us understand that there are still a lot of problems regarding the chemical sensors, in particular about the drift of the sensor's response during time. So we have tried to partially solve the problem with onboard local dynamic multivariate calibration, and this seems to reduce the error under PPB levels for some species, at least locally in time, so for a short number of weeks. Afterwards, the performance gets worse and worse. But this confidentially, this allow to confidently allow the user to obtain a qualitative personal exposure assessment, so what has been called in the presentation before an indicative index of the air quality. And this can be very helpful to the point that it is possible for us to pursue a business model to target government or private sector, for example, the real estate, by proposing a high temporal and spatial density 2D model based on just spatial pollution maps. And at the moment, we have contact with some private companies that want to exploit this kind of application, notwithstanding the open source approach that we have followed. So. So conclusion, we come to the conclusion. So in this work we propose the design on an ecosystem for highly distributed, maker-friendly and user-centric air quality monitoring system, and aimed to involve the citizen in this stage of in multiple stages of the monitoring process. Currently, we have designed and realized this prototype sensor box. It has been 3D printed with an open source design. It's mountable on bike and transportable on backpack. We have developed this Android app that we have presented today, and we have online a backend server capable to gather the data on the ENEA grid facilities. We allow the user to have a qualitative assessment of his own personal exposures, and we allow to share the data in a social way. For the future, we plan to close the on-field calibration experimentation to provide quantitative measurement, even if this quantitative measurement should be always thought about an indicative index. And we are trying to move to possible scenario with single board computers like you do, or Arduino Uno for cheaper and faster solution. And we are also moving to geospatial data simulation based model and provide the situation with the capability to provide more precise map by integrating data coming from a fixed station with data coming from the mobile station. So I'd like to thank you for your attention.